but in Chapter 7, we're going to do some IP introduction. But, you know, what's most interesting about this particular chapter is not the IP, it's the IPv6, right? Because a lot of people have exposure to IP. They have general understanding of how IP works, but they don't quite understand how IPv6 works. So I think that's what you're going to gain from the most part from this particular chapter here. It's not very long, and then the subnetting chapter is next, and then we're just going to wrap up with some routing and stuff like that. All right. IPv4 addresses are 32 bits in length, as you can see here, written in dotted decimal format. We did a little bit of discussion yesterday about how to convert from that dotted decimal format to a binary format. We use the radix scale, right? 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, etc. Each octet is 8 bits in length. So we essentially will evaluate each of these octets independently of each other. And that's how I teach subnetting as well. Subnetting is actually really only about working with one octet. Otherwise, it's very simple. A lot of people teach subnetting different ways, but I'll show you guys how I do it as part of this process here. Okay? So to do the conversions, you have your radix scale, 2 to the 0 to 2 to the 7. Remember what I told you guys for the exam? You want to be able to calculate numbers up to about 2 to the power of 13. So you want to write down that radix scale up to 2 to the power of 13 if you can. That will help out a lot. Now, as far as representing any IP address octets, we only need 8 bits to do that. So that's 2 to the power of 0 up to 2 to the power of 7. The place value that you see there, 1, 2, 4, 8, 16, 32, 64, and 128, these are essentially the weights of each of those values of the power of 2. Okay? When you want to represent a decimal number, you simply turn on the bits that add up to that particular decimal number. So what we see here is the 32 is on, the 2 is on, the 1 is on, so this is equal to 35, right? Because 32 plus 2 plus 1 is equal to 35. Very simple process. Very simple, straightforward process. And by the way, this is the same way that we would represent any number in binary based on a number in decimal. It's no different. It's the same process. In this case, we're only dealing with 8 bits because we're talking about an IP address. But you could be dealing with 16 bits. You could be dealing with 20 bits. It doesn't matter. The math is still the same. The process is still the same. All right? So if I want to convert decimal to binary, I do the opposite. I essentially turn on the bits that add up to whatever that decimal number is. If I already know the decimal number, I turn on the bits that add up to that decimal number. So a 192 is 128 plus 64. A 6 is a 4 plus 2, and so on. I think everybody here pretty much has a good understanding of this process, right? I don't have to go into a whole lot of detail on this. I think most of you understand that. All right. The other aspect of an IP address, though, and probably the most important aspect of an IP address, is its subnet mask. The subnet mask determines how that host functions on the network. An IP address without a subnet mask isn't that useful. You can't just randomly choose a subnet mask, though. There's a couple of rules for a subnet mask, and this applies to both IPv4 and IPv6. Subnet masks are broken up into 2 pieces: the network portion of the mask and the host portion of the mask. The network portion of the mask is always represented with consecutive 1s. The host portion of the mask is always represented with consecutive 0s. You will never see a subnet mask that has a mix of 1s and 0s. All right? And by the way, it's the same for IPv6. The only difference in IPv6 is that the subnet mask is longer. It's 4 times the size. 128 bits as opposed to 32 bits. You might see a subnet mask written in dotted decimal format. You see it up there, 255.255.255.0. Or you might see a mask written in prefix notation, slash notation. Some people call it CIDR notation. I don't like to call it CIDR notation because CIDR means classless. And actually, this mask is not classless. It is actually classful. But nothing wrong with calling it CIDR, I suppose. The actual technical term, especially if you move on to some of the more advanced classes, is prefix notation. That's really the official term, prefix notation. What does the slash or prefix notation represent? It's very simple. It represents the number of ones in the mask. If you see a mask with slash 18, there's 18 ones in the mask. If you see a mask with slash 12, there are 12 ones in the mask. In IPv6, if you see a mask with slash 120, there are 120 ones in the mask. All right? You guys are going to have to definitely, I'm lagging. You guys are definitely going to have to be used to prefix notation for the exam. Let's see. Oh, my CPU seems to be running okay. Let me shut down some stuff here. Could be the internet this time. It's not my computer this time. I'll see if it gets better, Giovanni. If it doesn't, we'll take a look. But so on the exam, you guys are going to have to be very used to dealing with masks in slash notation. You're going to see that quite a bit. So one thing that you need to become comfortable with is converting prefix notation to dotted decimal notation. In the next chapter, we'll see why that's important. All right? Prefix notation to dotted decimal notation. All of the math that we're going to learn, all of the calculations that we're going to do apply to IPv6 as well. You guys are not going to be scared of IPv6 once you're done with my discussion because everything with IPv6 is going to make sense. So as I said before, a subnet mask is only going to be certain values. 0, 128, 192, 224, 240, 248, 252, 254, and 255. You'll never see a 130 or a 144 because that's not consecutive ones and zeros. Does that make sense? All right. Now this table that I've created on the bottom right, if you can somehow create that table before you start your exam, that will save you a ton of time on the test. Because here's how it works. If you're given a prefix notation of, say, /13, all you have to do is say, okay, /13 is 248 in the second octet because /13 matches with 248. /20 is 240 in the third octet. Make sense? So you don't really have to kind of know anything. You don't have to know any of the math. Well, I'm going to teach you the math in case you can't recreate this. But this table is kind of a quick cheat sheet on how to go from prefix notation to dotted decimal notation. This only applies to IPv4, by the way. We don't use dotted decimal notation in IPv6. All right? So a /17. Yes, there are instances where /31 is used. For point-to-point serial links, a /31 can be used because you're not going to have a broadcast address. You'll have a network ID, but you won't have a broadcast address. There's actually instances where /32 is used as well. On loopback interfaces, we use a /32. All right. And by the way, you can see a /7, a /6, a /5, a /4. Those can exist as well. We use like /7, /5, /6, /4. We're going to use that in instances where we're doing things like route summarization, where we're summarizing networks together. All right. 19 ones in the mask is a 224 in the third octet. Now, if it's a 224 in the third octet, what does that mean it is in the first and second octets? 255. And what does it mean that it is in the fourth octet? 0. Exactly. One of the things to think about when it comes to subnetting and doing subnet calculations is that all you have to really concern yourself with subnetting is 1 octet. Because the rest of the octets are either network ID or host ID. I'll teach you guys that a little bit later on. So this table was very useful. As far as the actual bits, these would be the number of bits that are on in that respective octet to equal that corresponding mask value. So 2 bits are on, and we see that here, 1, 2. Or 3 bits are on, we see that here, 1, 2, 3, and so on. That's how you get the /12 or the /11, because you have 8 plus 9 plus 10 plus 11. All right, we're going to go through a lot of examples. We're going to do some calculations. We're not quite done here yet, but that table is very useful. Now, back in the day, am I still lagging, Giovanni, or does it sound better? Back in the day, we used to have this thing called classful addressing. The folks that came up with this concept, they said, well, we're not going to have too many people on the internet, so let's go ahead and define the mask that's going to be used with the address block. And what they did is they came up with 5 address blocks, class A, B, C, D, and E. And all of the vendors and all the manufacturers wrote their routing protocols to assume what the mask was based on the address range in the first octet. So if your address was anywhere from 0 to 127, you would have a /8 mask. And that was just assumed. We never sent the subnet mask information along with the routing updates. So we kind of assumed that, hey, if you have a 125 address, you must be using a /8 mask. Okay, this is what we call classful addressing. Any kind of address that uses its predefined mask is considered to be classful. Anything that doesn't use its predefined mask is considered to be classless. Classless is good. Classful is bad, because classful means no subnetting. Now, how did they actually come up with these ranges? All they did was they manipulated the bits in the first octet. All those green markers there indicate bits that don't change. So for class A, the most significant bit in the first octet is fixed at 0. For class B, the first 2 bits are fixed at 10. For class C, 110, and so on. Now, this all went out the window in about 1983. So it wasn't very long that classful addressing stuck around. People still kind of refer to classes, but actually classes don't really exist anymore. There really are no active protocols that are classful. RIP version 1 is the only active protocol that's classful right now. IGRP was classful, it doesn't exist anymore. EGP, Exterior Gateway Protocol, was classful, it doesn't exist anymore. So we don't really worry about this too much these days. But of course on the exam, this is something that they will definitely test you on, understanding the different classes. Notice that Class D is reserved for multicast, Class E reserved for experimental uses. There are some reserved addresses within these blocks as well. There are private address ranges. There are address ranges that are reserved for other functions within IP. But as far as the classes go, this is the breakdown of the classes. All right. Within IPv4, okay, we have predefined private address blocks. On the exam, these are going to be referred to as RFC 1918 addresses. RFC stands for Request for Comment. It is essentially a design document, or for lack of a better term, a technical paper on a network specification. All protocols have some sort of RFC tied to them. There's an RFC for TCP, RFC for UDP, RFC for EIGRP, etc. 1918 happens to be the RFC number for private addressing. This also was something that was developed because of the lack of address space in IPv4. So the powers that be decided that we're going to go ahead and allocate certain blocks within each class for private addressing, meaning that anybody can use these address blocks as long as you don't try to route them on the internet. They're still routable addresses. They're still valid addresses. They're just not routable on the internet. Okay? You can route them inside your network. You can actually route them anywhere as long as it's not on the internet. You will need to know these ranges for the exam as well. The entire 10 block, for example, for Class A. There's a subset for Class B, 172.16 to 172.31, and for Class C, 192.168. I'm sure you guys have seen this before. Nothing crazy about that. We do have some other reserved addresses in IPv4, though. The first address in a subnet and the last address in a subnet. Where does the first address in a subnet show up? It's called the network ID. Where do we see that? Routing tables. Network IDs allow us to identify the network that a device belongs to. The most prominent place you'll see that is in a routing table. The very last address of a subnet is a subnet-directed broadcast address. It's the address that we use to send traffic to any host within that subnet, to all hosts within that subnet. Those two addresses are reserved and can never be assigned to any device, the first and last. In IPv6, only the first address is reserved because we don't have broadcasting in IPv6. So the last address in IPv6 is actually usable. Another block predominantly used is this loopback address block. Most people are familiar with a loopback address as 127.0.0.1. If I ping 127.0.0.1 and I get a response, what does that tell me about that device? What is that actually testing? Any ideas? It is testing the protocol stack. It's testing the software on the computer. It's not testing the network interface. You can have all your interfaces disabled, and it will actually still ping. If you ping a 127.0.0.1 address and it fails, then you have an issue with your software. It doesn't indicate any kind of failure or success with an interface. All right? All it simply does is it allows us to test the protocol stack of that device. Well, whoever decided to set up that feature decided that they were going to use the entire 127 block for that feature. So actually, you can ping any address in the 127 range, and it will give you the same result. That's 16 million something addresses to do one thing. They didn't really think that address space was going to be an issue at the time, I suppose. Another type of address is called an Ipv4 address or a linked local address, 169.254. Generally speaking, a client that gets a 169.254 address is not going to be able to communicate. We typically use 169.254 for things like diskless workstations, where they don't even have an operating system. What they do is they will go out and they will boot up on the network. So they'll give themselves an address in the 169.254 range, and then they'll use that subnet to communicate to their to get their operating system. You will see this from time to time. If a client doesn't have a static IP and it can't get to DHCP, it will actually assign itself a 169 address. For the most part, this is considered to be useless. Okay? Although it does have a function, it does have a function defined. The experimental class, of course, we talked about that. Pretty much not used today. And then the all-host broadcast or all-network broadcast address is 255, 255, 255, 255. That's used quite a bit for things like DHCP and other protocols. Most of the time, routers will block that. You can ping that address, but it doesn't work all the time. All right. I hear something, but everybody's muted. I don't understand who I'm listening to. Flower Chantel. Who is Flower Chantel? I don't know why I can't mute Flower Chantel. Okay. Oh, now they're muted. Thank you. As we talked about before, classful addressing means you follow the rules that were predefined. All right? Classless addressing is the opposite of that. Classless means you don't have to follow the rules. You can use any subnet mask you want for any address block. This is what we would basically refer to as subnetting. All right? Technically, it's called CIDR, classless interdomain routing. The reason it's called that, though, a lot of people aren't aware. Because what does routing have to do with it? Well, back in the day, the original routing protocols did not send subnet mask information along with the routing updates. So we always had to assume the subnet mask. When they started updating these routing protocols, they started making the routing protocols send the subnet mask information so that we could do the math and figure out where a host belongs, how it's communicating, etc. So that's why it's called classless interdomain routing, is because the routing protocols changed to support this subnetting concept. All right? Who assigns these addresses? Well, we have 5 regional internet registries. Of course, we know who the top guy is, right? The chief of all of them is the IANA, right? Internet Association for Numbers Assignments, or whatever the heck it stands for. But the regional internet registries, these are the guys that are responsible for handing out addresses in their respective region. None of these guys have any V4 address space left. That was gone in 2013. So you can only get V4 space from your service providers now. But these guys are still handing out IPv6 addresses. All right? 75% of all of the public V4 address space is owned by ARIN, because the United States is kind of where the internet started, right? And that's where a lot of the address space was allocated initially. In IPv6, it's a little bit different. It's more widely distributed, but I will say, as far as IPv6 prefixes go, the vast number of, or majority of IPv6 prefixes is actually in the United States. You can go out and see how the allocations are, or how the prefixes are allocated, but we'll talk a little bit more about that as we move through the rest of the chapters here. Okay? So why IPv6 then? We seem to be moving along quite well with IPv4. Well, IPv6 obviously is going to provide us the ability to have a lot more addresses, right? IPv4 was depleted back in 2013. No more IPv4 address blocks with our regional internet registries. Also, NAT, network address translation, was not really designed to be part of IP. NAT was a stopgap measure to kind of stop the bleeding from IP addresses being depleted. Remember, IP didn't originally have NAT defined. We didn't have network address translation defined because we didn't have private addressing defined. It was only after private addressing was released, RFC 1918, that NAT became a necessity. All right? So we've kind of moved on to this IPv6 space. An IPv4 address is 32 bits in length, as you can see. 4.29 billion addresses. Seems like a lot, but it's not really. IPv6 addresses are 128 bits in length. 340 undecillion addresses. 3.4 times 10 to the power of 38. Okay? IPv6 does a lot more, though. We talked about that in the last chapter. When we did our introduction to IP, we were talking about how IPv6 has IPsec built into it. It doesn't have broadcasting. There's no private addressing. It's all public addressing and so on. So quite a few changes in IPv6. What if I want to switch to IPv6? What kind of options do I have? Actually, there's about 5 or 6 different options that you have. I'll mention only a few of them because that's what's relevant for the exam. You can do dual stack. We're actually going to set up dual stack routers tomorrow. Dual stack is where you're running both protocols at the same time, IPv4 and IPv6. Believe it or not, almost all of the service providers in the United States today are handing out IPv6. You just don't know it because your router's not programmed to work with IPv6. But if you have Comcast or AT&T, Verizon, whatever, you can get IPv6 addresses now. All right? Even our web servers, Think Tank's web servers are dual stack. We have IPv6 and IPv4 on them. And of course, all the important pages like Facebook and Twitter and all that other junk. All right? So dual stack is just the concept of running both protocols at the same time. You can do some translations as well. You can do 6-to-4 tunneling. Let's say your service provider doesn't support IPv6, but you want to run IPv6 inside your enterprise. You can actually tunnel IPv6 traffic inside of IPv4. You would just carry it as payload. That's called 6-to-4 tunneling. And there's some other tunneling methods. There's Teredo tunneling, ISATAP tunneling, ISATAP. Those are host-based tunneling mechanisms. You can also do NAT protocol translation. You can convert from v4 to v6 using a NAT 6.4 router. So lots of different techniques for moving from IPv4 to IPv6. The most common technique is dual stack. The downside to dual stack, though, is that you're doing everything twice. If you're running routing, you've got 2 routing instances. If you have ARP caches or ICMP neighbor caches, you have that twice. So that's the downside to dual stack. You're kind of running things twice. An IPv6 address, as we mentioned before, is 128 bits in length. Now we know that IPv4 addresses are represented in 4 octets. 4 octets, meaning 4 blocks of 8 bits each. IPv6 addresses are represented in 8 hextets. 8 hextets. Hextet is a 16-bit field. Now people look at that and they go, oh man, I don't want to run IPv6. If my address is 10.1.1.1, that's a heck of a lot easier than saying 2001 0DB8 00001111, etc. But I'm actually going to tell you guys that I'll show you guys in the rest of this chapter that that's not really how IPv6 addresses work. It's actually a lot simpler than it sounds. Yes, that is how an IPv6 address is written. It's written in hexadecimal format. There are some techniques that we can use to shrink the size of that address, but also the way the addresses are represented globally makes it a lot easier to handle as well. I'll explain that in a minute. All right? Two things that you can do to shrink an IPv6 address on paper. First of all, leading zeros in each hextet are optional. They're always there. Computers know how to interpret that, but you can take out the leading zeros, not the trailing zeros. If you took out the trailing zeros and the leading zeros, how would you know if it's 0100 or 0010? See what I'm saying? So you can only take out the leading zeros. That helps a little bit, right? Instead of 0DB8, it's going to be DB8. Instead of 0000, it's just 0. So that shortens our address a little bit. The second thing that you can do is you can represent the largest consecutive blocks of zeros with a double colon. All right? But this has to be done in hextets. You can't take 2 zeros from one and then 16 zeros from another and take them out. All right? So if I go back to my previous example, where is the largest block of consecutive zeros here? The 5th through the 7th hextet, right? So I can actually take out all of those zeros. That's 48 zeros. And I can just put in a double colon for those 48 zeros. 48 binary zeros, right? All right? So by combining those two things, and by the way, the double colon can only be used once because it doesn't represent a specific number of zeros. It represents whatever's left over is zeros. That's a compressed address. All right? You can use the double colon anywhere you want, as long as you don't use it more than once. Okay? So the example you see at the top, example number 1, you've got 32 bits of zeros on the left, you've got 32 bits of zeros on the right. So you can choose to use the double colon on the left, or you can choose to use the double colon on the right. Doesn't matter where it's used. But it can only be used once. All right? In IPv6, no more broadcasting. We already talked about what unicast is, what multicast is, what anycast is. But no broadcasting in IPv6. All right? Simple enough. In addition, we use the subnet mask in IPv6 just like we did in IPv4. The subnet mask does exactly the same thing in IPv6. It tells you what portion of the address is the network and what portion of the address is the host. And it's the same. It's ones are the network, zeros are the host. All right? We do not use any kind of format to represent a v6 mask other than prefix link. Prefix link / notation. Remember I told you guys the technical term is prefix, right? When you look at a routing table, you look at prefixes. The prefix length allows us to identify the length of the mask. Okay? Couple of reserved addresses in IPv6. Some of these you'll have to know. There are no IPv6 questions on ICND1. Very few IPv6 questions on ICD2. And again, I'm talking about the old version of the test. The new version of the test, they have IPv6 on both exams, but it's kind of very basic, okay? Now, let me break this down a little bit for you guys, because this is where it gets really, really interesting, I think. With IPv6, let me pull up Notepad here. I don't need to, just open it, all right? With IPv6, you guys know with IPv4, the way that we broke up our addresses is we said, okay, the first octet identifies the class of the address and so on. So that was 0 to 255. Make sense? In the first octet. In IPv6, it's the first hextet that identifies what type of address it is. So actually, we go from 000 to FFFF. That is the range of IPv6, 0000 through FFFF. Most of that address space is reserved for future use. It's not defined, it's not being used. 2000 :/3 is the only address space used for routing today. Okay, so that means that 0000 :/3 is reserved, and then we've got that takes us up to the 2, and then we've got 4000 :/3 reserved, and so on. So there's still a lot of reserved address space that's not being used for anything today. This is my public routing domain. So every single IPv6 address on the planet that is routed on the internet falls within that range. So let's talk about what that means. 2000 is 0010, 0000, 0000, 0000. You guys agree with that? Remember, 2000 is hex. And I converted that hex to binary. Shake your head yes? Okay. The /3 means the first 3 bits are fixed. They're part of the network, which means that the remaining bits are not fixed. X. You guys follow me so far, right? So the usable global address routing range is 2000 through 3 FFF presently. That's how I got up to 4000 as the next block. That's how I got from 0 to 2 as the first block. Does everybody understand how I got this here? Does anybody understand? If these bits can be anything, if this bit is a 0, the value of the first hexadecimal number is a 2. If this bit is a 1, the value of the first hexadecimal number is a 3. You follow me? If these bits are all 0, the value of that hexadecimal number is 0. If these bits are all 1, the value is F. That's how we're defining the range. Because whatever has an X next to it can change. You follow what I'm saying? It's kind of like saying 0 to 127, right? How did we define 0 to 127? We fixed the first bit at 0, and then the remaining bits could be anything. And that's how we defined the first range. And then we had 128 to 191. Well, that's because the first 2 bits were fixed, and then the remaining bits could be anything. You guys follow me now? it's kind of beyond the scope of what you guys actually need to know. Can you guys still hear me online? Nobody's saying anything online, so hopefully you guys can still hear me. Okay, good. All right, so bottom line is every one of the prefixes that are assigned globally fall within that range. And that's what they're defining here, the global range. Global means routable on the internet. All right, assigned by the IANA as public networks. Okay. Now there's some other networks that are reserved. The loopback for IPv6 is :1. That's a little bit smarter, right? Just being :1. Because remember, in IPv4, it was anything that's 127, right? But in IPv6, it's just :1. It does the same thing, but it tests the protocol stack for IPv6. And then unspecified is :. Isn't :, just all zeros? Exactly. All right. Multicast is a very important part of IPv6 as well. Multicast addressing. There are some well-known multicast addresses that you're going to have to know, but all IPv6 multicast addresses start with FF. All of them. Okay? Now, we're not going to get into the whole scoping of multicast. The 02 is actually a site local scope, and then there's a 01, and there's different scopes, but don't worry about that. If you see an FF address in IPv6, it's multicast. :1 is basically like a broadcast address for IPv6. Every single IPv6 host participates in :1. So if you want to send traffic to all IPv6 hosts, send it to FF02 :1. Why the :? I mean, that looks like a pretty short address for IPv6, doesn't it? It's just a bunch of zeros, right? If it's an IPv6 router, it's going to be FF02 :2. If it's EIGRP, FF02 :A. If it's OSPF, FF02 :5 and :6, and so on. So as I mentioned before, global unicast addresses start with 2000 :/3. Now, this is the part that makes IPv6 even more interesting, right? Because let's break this down. The regional internet registries are getting assigned /23s. There are some legacy addresses that are smaller than that, but a regional internet registry is getting a /23. Remember those 5 regional internet registries? Who's giving those regional internet registries a /23? IANA, right. So let's do some math here. That means that I have 2 to the power of 23, 8,388,608 prefixes. All right, 8 million prefixes. I'm going to put that in Notepad. Oops. This goes to my regional internet registries. The regional internet registries are then subnetting these prefixes down to /32, and that's what the ISPs are getting within the region. So your ISPs are getting a /32. Within each regional internet registry then, how many /32s can I get? Well, if I take 2 to the power of what? Not 32, 2 to the power of what? So 2 to the power of 9. So that's 512 prefixes within each region for the ISPs. Now you might look at that and go, well, that's not a whole lot of networks. But remember, there's 8 million of those prefixes that are available for the regional internet registries, and for each of the 8,512 subnets. It's a lot, okay? Then, as a business, you want to go get an IPv6 prefix from your ISP, you're going to get assigned a /48. Now we're talking about 16 bits difference. That's 65,536 additional subnets. So for every one of the 512 networks, you have 65,000 choices. And for every one of those 512 subnets, you have 8 million choices from the regional internet registries. Now you're starting to get the idea of the scope of IPv6. It's a massive, massive address space. All right. We're going to forget about the /56. We're going to focus on the /64. Because here's how it works. Remember I was saying that an IPv6 address is 128 bits in length, but for the most part, you only have to worry about the subnet and the host. From /48 to /64, that is your subnet. That's 65,536 subnets. So here's what's going to happen. As a company, you're going to get an IPv6 prefix, and maybe it's 2001:ACAD:056B. That is your company-wide prefix. Make sense? So essentially, throughout your entire organization, the first 48 bits of every single network is the same. So you can kind of forget about the first 48 bits, right? What's the first network going to be? Probably going to be 0001. Actually, it could be 0000. What's the next network? 0001, 0002, 0003, 0004. That's how you subnet IPv6. These are bits 49 through 60. Well, it's the fourth hextet. We'll just put it that way. So let's say you call Bob and you say, hey, Bob, you're having a network problem. What building are you in? Oh, you're in building X? You're in subnet 2, right? You don't have to worry about the first 48 because every building has the same first 48. You're just going to say, oh, building X is in subnet 2. Make sense? So even though, and by the way, you can go all the way from 0004 all the way up to what? FFFF. Make sense? So the network ID actually is broken down into just 4 hexadecimal numbers. Then the host portion is the last 64 bits. And by the way, you can do the hosts like this. :1, :2, :3. Doesn't have to be all 64 bits. You see what I'm saying? So in reality, somebody's actual network address might be 2:1 or AC:A. You see what I'm saying? Because you can forget the first 48 bits. You're not going to use all 64 bits of the host range. You're going to use consecutive numbers within that range. So when it comes down to it, if you do your subnetting correctly in IPv6, the addresses can actually be easier than IPv4. Right? Because your address, your fully qualified address becomes this, and that's your subnet mask. And by the way, no more /30s, no more /27s, no more /25s. Everybody gets /64. Is your company going to need more than 65,000 subnets? Probably not. You can subnet beyond /64, but most people don't. They stop at /64 because you're going to get a 48 from your service provider. You're going to subnet this /48 down to a 64. So point-to-point serial link, give it a /64. We don't have to worry about, there's 510 hosts, so I need a block of addresses that is this big. I just give it a /64. If you guys get IPv6 at home today, that's what your service provider is giving you. They're giving you a /64 at home, which means you have 2 to the power of 64 public addresses. It's a lot of public addresses for your house, right? This is beyond what you need to know for the exam, but I want you guys to understand the differences between V4 and V6. Does this kind of make sense? I guess the question then would be, why 64? Why did they pick 64? Well, we'll talk about that in a minute. Okay? So interface ID is actually just the host address. So the subnet mask is 64, which means that this portion is the network, this portion is the host. A lot of people say that there is no subnetting in IPv6, and that's absolutely false. There is subnetting in IPv6. It's just not the same. I mean, mathematically it's the same. We don't think about it the same way. I had an engineer call me about a year ago and said, hey, we're doing IPv6. This network is a /30, so I want to use a /126. But now I can't figure out where my networks go and where they end and where they begin. I said, why are you going to use a /126? Just use a /64. And I had to convince him he wasn't wasting address space, even though he is. It doesn't matter. All right? All right. Oops. Not if you follow this basic rule, right? Have your networks consecutive in that fourth hextet, 000 through FFFF, and then for your interface IDs, just use consecutive addresses for your interface IDs. I mean, you always have the possibility of having duplicate addresses no matter what, right? That's always a possibility. Whether it's IPv4 or IPv6, it doesn't matter. I don't know if you guys have seen this representation of IPv6 before, but the one thing that people get the most concerned about when it comes to IPv6 is the length of the address. And what I'm trying to impart on you guys is that the length doesn't really matter, because ultimately it's not really going to be that long. All right. For example, this is our network, right? That's half of our network. On the addresses, this is the site prefix. So every interface in my network gets this 2001 DB8 ACAD. So the network ID for this interface is 1, and the interface address is 1. So if somebody asks you what network you're in, you just say 1:1. Notice the site ID here is the same. So you can, I mean, you still have to know that, right? It's still part of the address, but if it's the same throughout your entire enterprise, this is the network and address on interface 1, interface 2, interface 3. And because you're not worried about, is it a /30, is it a /24, is it a /29, it makes it much easier because you're not worried about how many hosts per interface and whatnot. Okay? Now hosts themselves, this is even better. What a host does is it can self-allocate its own address. It's called auto-configuration, stateless auto-configuration. Essentially what the host does is it uses its MAC address to derive its host address, and then it sends out a router solicitation message saying, is there a router on the network? the router responds with, yes, I'm a router, you can use me, and the router essentially advertises to the host its network ID. So the host just joins the network automatically based on this auto configuration process. All right? So this is kind of how it works. Here's my link address. The link address, remember, is the host ID. So the host sends out this, and by the way, this is all done with ICMP, Multicast. The host is basically advertising to everybody, here is my link ID, which is my host ID. All right? And by the way, this is what replaces ARP. It's ICMP neighbor discovery. All right? This would be after the router or the host has joined the network. And by the way, the host can now also be a member of multiple subnets. Because in IPv6, you can have more than one address on an interface. The host can be a member of more than one subnet. It's a very interesting concept. Why /64? Well, /64 came about because when they developed IPv6, they said, let's find a way, because AppleTalk did this, let's find a way to allow the clients to assign their own host address without any intervention from any other process on the network. And they did that by using the MAC address. MAC addresses are globally unique, right? They're supposed to be. So if I use the MAC address to derive my host ID, then that should also be globally unique, right? The problem is a MAC address is 48 bits. The host address is 64 bits. So what do? Take the MAC address, split it in the middle, and drop in an FFFE. That's constant, right? FFFE is always put in the middle in an EUI64 process. EUI64 is what they call this process. It's basically automatic host ID calculation. And then the last thing you do is you invert the 7th bit. So in the MAC address, that 7th bit is always going to be a 0, isn't it? Because that's the UL bit. That's the unique or locally defined bit. Remember those 2 bits that were reserved in the MAC address? The IG bit and the LG bit? That is the IG bit, right? Or LG bit, excuse me. So that's how a host will derive its interface address from its MAC address. I could demonstrate that real quick. Windows does something different because Windows randomizes that process for security purposes, but on a router, that's not the case. Let me go ahead and pull up a router here. All right, I'll just do a quick demonstration here. We're almost done with this chapter. The last chapter we'll do today, I know we're past our 5 o'clock time, but you know, we won't be much longer. We're going to do the subnetting next. So config T, IPv6 unicast routing. That's what enables routing, IPv6 routing on a router, by the way, IPv6 unicast routing. Interface FA01, IPv6 address 2001 /64 EUI 64. Now I could assign the address statically on the interface, and that's usually what I'm going to do in most cases. But what I've told the router to do in this case is use this as the network ID, which by the way is 2001 :0000 :0000 :0000. That's the first 64 bits, right? And use the EUI64 process to assign the host address. So if I do a show IPv6 interface brief, you can see that the address became this. All right, well, let's see how that actually came about. I'm going to copy that. put that in Notepad. And I'm also going to do a quick show interface FA01. And I'm going to copy the MAC address of the interface. So that was the MAC address. This is the EUI64 address. Well, how did I do it? 0001 6481 2502, right? Split that in the middle, put in the FFFE. That takes me from 48 bits to 64 bits. You guys agree? All right. And then I invert the 7th bit. The 7th bit happens to be in this. Remember, these are hexadecimal numbers, right? 0000 00x0. This is 4 bits. That's 4 bits. That's 4 bits. That's 4 bits, and so on, right? So if I invert this bit, it's 0 originally, but if I invert it, it becomes that. Sorry. Which means that this becomes 02, doesn't it? You guys agree? And guess what? 02, 01, 64, FFFE, 81, 2502. So that's how this host portion, the leading 0 is missing, right? Because we can drop that. But this is a derivative. This host address is a derivative of that MAC address. And by the way, the fully qualified address is actually this. That's the whole address. This is the network ID. This is the host ID. I guess I should put in the /64. That's the address. Of course, I can replace all of these with double colon. I can get rid of that leading 0, and that becomes the host address. As you can see, using the EUI64 process for a router interface is probably not a good idea because you have to remember that random address. But for a host, that might be okay. All right. All righty. All right, just another example of that link local process. Here's the MAC address. Here's the link local addresses. All right. Let's see. I think we're okay with that. Let's get into, I'm not even going to take a break. Let's just go ahead and wrap up. I know this is the chapter a lot of people online are wanting to see.